Ladies and gentlemen, in this video, as in the other videos, I've kept telling you about hybridization theory that takes place outside of carbon. So now we've spent a couple of minutes, maybe a few more minutes than what you wanted, to talk about carbon hybridization theory. But you know, nitrogen can have hybridization. It's a common piece of an organic molecule. Oxygen can have hybridization. It's also a common piece of an organic molecule. So we can't leave those out. We at least want to address them. Maybe not in as much detail as carbon, but we can at least talk about them in the same way. So if I drew the electron configuration of nitrogen, I would write, hold on, let me center this back up. I got a little crazy with my pen. All right, 1s2, 2s2, and 2p3. That is the electron configuration of nitrogen. There we go. So if I wanted to draw the box diagrams, there's my first one, and then here's my second, and then my third is here, 1, 2, 3, and there we go. So the issue here is that normally nitrogen would have 3 bonds, right? And then it's got a free pair of electrons. We said that this was the notation of hydrogen almost every time because this is what provides nitrogen a formal charge of 0 whenever we can get it. So this is a very stable form of nitrogen. So with that said, there's another issue here. And the issue is that if this was the case, if nitrogen really was this setup, then we would look at this set of electrons right up here at the top, and we would regard that as a 4th bond in a way. And we would also look at these bond angles, and the bond angles here would be 109.5. However, when we actually study the structure, we see that the bond angles are not 109.5. Which means that this is not in its traditional form. This is actually 107. So it's slightly off. Now, it doesn't sound like a big deal, but they really have an issue with this because if it was truly this setup, then it really should be like everything else, and it should be truly tetrahedral with a 109.5 degree, and it's not. So hybridization exists here as well. This is the S, and here are the 3 P's. Hybridization exists all the way across, it morphs in, and it gives us still an sp3 hybrid. Now, you're probably thinking, well, how do we do that? Normally, we erase an electron. That's true, you do. And then we write the electron in an extra box somewhere. But none of these bedrooms are empty. It's nowhere for it to go. Well, sometimes we can put it back where it came, so it can share that bedroom for a little bit. And then sometimes we can slap it here, and it can share that bedroom for a little bit. And then if it gets tired of that and they don't get along, they can go to the next bedroom and try to get along with that brother or sister, and that doesn't quite work out for them. So we have choices. That's how I want you to look at this. So this also shows hybridization. It's still an sp3 hybrid. So all 4 of these bonds actually are the same. And if we do this, if this does become a truly sp3 hybrid, then we do route back to an NH3 with a free electron pair that has now reset itself back at 109.5. Okay? So, this is the accepted way that nitrogen is. If you see nitrogen, and nitrogen has 3 bonds, and the 4th is a free pair of electrons like this, we regard that as 4 single bonds. And those 4 single bonds, just like with carbon, are sp3s. That's how we determine if nitrogen is a hybrid, and if so, what type of hybridization is it going to be. So 3 bonds with a free pair of electrons, that is what we call an sp3 nitrogen. Oxygen is also another commoner. Okay, oxygen is going to be 1s2, 2s2, 2p4. So in the boxes out here, we have 1, 2, 3, and 4, and then here's a box with 2. If we look at this, electron configuration, and we accept the fact that two of these electrons can be floaters if we morph all of this together, then we have an equal sharing in space of those electron bonding pairs, but only if those are hybrids. And that hybrid again is an sp3. So if oxygen has with it two bonds like we've always drawn and two sets of electrons like this is going to be regarded as an sp3 oxygen. Keep in mind, this is a single bond, that is a single bond, this is going to represent a single bond, and that one represents a single bond. Even more so, look at the electron configuration, folks. We have a pair of electrons here, and we have a pair of electrons there. There's one pair, here's the second pair. Two others are going to be available for bonding. So if oxygen gains another bond, or if it loses a bond, then the hybridization begins to change. But under normal circumstances, oxygen with two bonds and two pairs will be sp3 hybrids. If I go back to nitrogen and I look at it one more time, 2s2, and then I have 2p3, 1, 2, 3. We said that these are hybrid and they form an sp3 hybrid. Nitrogen has three bonds, 1, 2, 3. That's because there's three available units that are here for a bond to form. The other two are part of bonding. It's a set, and we drew one set of electrons right up there at the very top. And folks, look, there's the match. So nitrogen with three bonds and a one set of electrons is a sp3 nitrogen. These are the normal states. This is how we show up. This is how we've always done formal charge. It's just a different spin using hybridization to explain why these structures are the way that they are, other than just formal charge, and that's it. So don't let these throw you off. Nitrogen with three bonds and a free pair is an sp3, and oxygen with two bonds and two pairs are going to be an sp3 as well. That is their normal state, and that normal state represents the sp3 hybridization. Now, the next question that you should have for yourself is, do nitrogen and oxygen, do those atoms have sp2s and sps as well? And the answer is yeah, they can, and it really follows the same trend that carbon does. So once again, do not let it throw you for a loop. So for instance, carbon has four bonds, that's its normal state. That is what we call sp3. Nitrogen will have three bonds. That's its normal state. Therefore, we call that an sp3. Oxygen has two bonds. That's its normal state. So that's what we call sp3. However, if carbon forms a double bond, then we call this an sp2, don't we? Well, guess what, folks? It doesn't really change. If nitrogen has a double bond on it, then we also call that an sp2. And if oxygen has a double bond on it, then we also call that an sp2. There is no difference in this setup at all. Carbon, if it had a triple bond, we called that an sp. Nitrogen, if it has a triple bond, guess what? We call it an sp. And oxygen, if it has a triple bond, we would call that an sp as well, but I'm not even going to draw it out because this is something that we are not going to commonly see ever in this first semester of organic chemistry. So I'm going to save you the trouble. I'm not even going to write it down, and we just assume that that's really the only two choices that we're going to see oxygen with. Okay, so that's all there is to it. Look at the number of bonds that are assigned to those atoms, and if they give you something like nitrogen or like oxygen, don't let it throw you off because you treat it the same as you do those carbons. So let me give you an example just to clear up any confusion that you might have. So here are some examples for you on the screen. And we're going to go through and we're going to label these with the hybridization that's associated with each one of those atoms. Now we're focused on carbon, and we're also focused on the nitrogens and the oxygens. They want us to label all of them, not just carbons. All right? So if I take the first example up here at the very top, this carbon, like usual, has 3 hydrogens, and the 4th bond comes from the bond to the nitrogen. So there's 4 single bonds right there. This is an sp3. This nitrogen, well, there's all single bonds all the way around it. That's all that matters. This is an sp3 nitrogen as well. If I go down to the next one, look how easy that was. If I go down to the next one, number 2, this carbon, all single bonds, sp3. This carbon, all single bonds, sp3. This carbon has a double bond, that's an sp2. That nitrogen has a double bond, guess what? It's an sp2. This nitrogen has single bonds all the way around it, that's an sp3. That's all there is to it. That's all that you got to do. Look how quick I did that, and you can do them as quick too. Number 3, this carbon, all single bonds, sp3. This carbon has a triple bond on it. That means that's an sp. That nitrogen has a triple bond on it. That's also an sp. That's it. Now I'm done with that one. That took literally seconds in order to do. Number 4, up here at the top, that carbon, all the way around, single bonds, that's an sp3. This oxygen, single bonds all the way around, that's an sp3 as well. Next one, number 5. I label everything. All single bonds, sp3. All single bonds, sp3. This carbon has a double bond on it. That's an sp2. This oxygen has a double bond on it. That is also an sp2. That's all there is, folks. Hopefully you are getting more comfortable with these. Hopefully you're seeing that these are a little bit easier than what you thought originally, and if so, you're learning. And that's really all that matters in this class. I want you to learn. I want you to understand that organic chemistry doesn't have to be nasty and ugly and hard and difficult. This is a process. You learn the process, you learn the rules, and you apply them. That's all that you have to do in order to do well in this class. So there's some more examples on hybridization theory that focuses on nitrogen and on oxygen.